Hello everyone, I hope you all are doing extremely great. Today we will discuss lead code question number 3620, network recovery pathways. So in this question we have been given a directed acyclic graph which has n nodes and all of these nodes are one indexed. Okay, so we have the information of a directed acyclic graph. Also we have some information about these nodes, like which node is online, which is shown as true in this boolean vector online, and which nodes are offline, which are shown as false. Okay, also they are saying that any path which starts from 0 and ends at n-1 is valid if all the nodes that are lying on that path are online and the total recovery cost of all the edges on the path are not exceeding k. So which simply means that this sum, like if I'm going from 0 to 2 and then 2 to 3, this path will have the edge weights as 3 and 4. 3 plus 4 is 7. 7 should be less than k, right? So here it is valid, then we are good. But on this path 0 1 3 we have the total as 15, which is not less than 10, so this path is invalid, right? Also this question says that for each valid path we have a score defined as the minimum edge cost along that path. So for any path the score basically means that the minimum edge cost which is there along that path. For example, if I have this 0 to 2, 2 to 3, right, this is the minimum edge, right? Along this path we have this edge 3, right? So yeah, now what we have to do for the given directed acyclic graph, we need to return the maximum path score among all the valid paths, right? So from 0 to n-1 there can be many paths, so out of them we have to return the maximum path score for any of the valid path, right? So out of all of them, one of them will have the maximum score, right? So any of them will have the maximum minimum edge weight, so we have to return that edge weight, right? This is the task for this question. Okay, let's discuss example number 2 here. Okay, so in this question we have this acyclic graph, directed acyclic graph, and this node 3 is offline, which is given in this boolean vector. As you can see, this node 3 is offline, so we can just ignore this node, right? We can just simply ignore this node. Great. Now starting from 0 and then ending at 4, we have technically we have two paths. One is this and the other is this, right? If I'm going through this path, we get the sum which is 12, right? Now this 12 is less than or equal to k, so this path is valid. Also this path is valid because 6 plus 6 12, again less than or equal to k, so this path is also valid. Now this path from 0 1 4 has the score as 5, whereas this path has the score 6. Minimum edge weight here is 6 and the minimum edge weight here is 5. Now out of these two paths the maximum value will be 6, right? Which means that this 6 is the answer, right? Okay, great. So now that we have understood the question, let's discuss how can we solve this, right? So there is one approach which goes using binary search. What we have to do is we will first binary search over this score. Okay, let's binary search over this score. Also let's draw a graph. Okay, give me 1 minute. Okay, yes, we have this graph like this. Okay, we have these sort of edges. Okay, great. Also let's assume we have this edge also here. Very fine. Now I'll just add the edge costs here. 3 2 2 1 4 3 and again 4. Okay, we have this, and these are like let's say this is 0. Oops. Okay, I'll just write them 0 1 3 and 4. Okay, now let's binary search over all the possible edges. Okay, let's say we have a range of this edge, these scores, right? From 0 till, let's say, something. Okay, and then we found a mid. Let's suppose this mid is 5. Okay, then we will check if this 5 score is attainable. This 5 score is attainable as the maximum possible score of any path. Okay, so now if this score 5 is maximum, which will mean that all the paths which have a edge weight less than 5 will not be considered. Okay, so for this check, we will remove all those edges from the graph, and then we will check if a path exists from 0 to 4. Also, that path, if that path sum does not exceed k. Okay, we will check these two things. First will be if the path exists, and the second, the total sum of all the costs along that path should not exceed k. Okay, so let's check for 5. Okay, now what we have to do, we have to remove all these edges, right? So which will technically remove all the edges, because every edge is less than 5, right? So we will not have a path, which means that 5 is not a correct. Then we will binary search between 0 and 5. Let's say we came across 2, then we'll check for 2. 1 gets removed. Okay, now great. And let's say case 6. Let's say case 6. Okay, I am not saying anything. Let's say case 6. In fact, let's place k to be 8. Great. Okay, or 6 is great. Okay, now we are checking for 2. Then for 2, what we will do, I have removed all the edges which are lesser than 2, and then we'll check if a path exists. Yes, a path like this exists. This path is more than k, so it is not correct. This path will have the sum 4 5 6 7 8, which is also not correct. Okay, nice. But we have this path has the total length as 5, so 5 is less than 6, which means that this 2 can be one of the edge, can be one of the scores. Okay, great, this can be one of the scores. So what will I do, I'll just now check between 2 and 5. Okay, let's check for 4. Okay, now I will check for 4. I will check for 4. So now in the case of 4, we will have all these edges removed, right? We will have all these edges removed, which will result in no path between 0 and 4. So this 4 is also not good. Now between 2 and 4, 3. Let's check for 3. We will remove this. Okay, now if I am removing all the edges lesser than 3, then do we have a path? Let's see. Yes, technically we have a path, but this path is not valid because 7 is bigger than 6, right? So this path will not work, so which will essentially mean that my answer will be 2, right? So in this way we will perform this binary search, right? And why will this work? Because if I am considering a score to be valid, okay, if I am considering a score, let's say we have a score as S, right? If we have this score as the maximum possible score for any path, which will mean that there is no path which has a score lesser than this, right? There is no path which has a score lesser than this, so there are no edges which have lesser than this S. And then we will check if we have a path existing or not, right? That's what we want to check. So we will check first if a path with score 1 exists. Yes, then 2, right? Now this will have a monotonicity, and we can just use binary search here. So yeah, let's now also start with the coding, which will help us get this understood a little bit better. So we have an edge, so we have a list of edges here. We will convert this into a graph first, but before that we can just do this inside the predicate function of the binary search itself, right? So let's write the predicate function here. Maximum edge. Okay, let's create the graph. Also, we will only take those nodes which are online, because the nodes which are not online, there is no point of adding them, because they will not be contributing to any path, right? So if online e of 0 and online e of 1, and if this is online and this is online, and the edge length is more than or equal to this max edge. Oh, this will be min edge, sorry, this will be min edge, and e2 is bigger than or equal to min edge, then I will add this edge into our graph. Also this will be a, because as this is a weighted graph, we will need a pair here. Okay, we are done with this. Now let's do Dijkstra, right? What we have to do for each predicate function, for each value of the minimum edge, we will check if a path exists between 0 to n-1. Now to check if a path exists which does not exceed k, we have to find the minimum shortest distance between 0 and n-1. So for that we can use Dijkstra. Making a min heap here, and distance array. Great. Okay, also we are starting from 0, so I'll just push this. Eq dot, also updating the distance of 0 to be 0. Right. If we have already arrived at any node, if distance or I'm just doing classical Dijkstra, right? I'm not doing anything fancy. if this node is if any neighboring node gets a better distance through my current node, and will be and this new distance all right. Also, if we arrive at return, then we have a valid path in, right? But if not, now we'll just now let's binary search over this. And then we just return A. Okay, let's run this. Okay, okay, it is giving a wrong answer somehow. Let's see why. Okay, because why are we getting 5? Okay, let's debug this code. Okay, let's see what's the fault here. If distance of current node is less than, okay, I think the implementation of priority queue is correct. Okay, okay, oh, we have to update it here. Okay, yep, we got accepted. Let's fetch some more test cases. Maybe someone has added. Yep, has anyone added something? Yep, one person has added one test case. I'll just add it here, and then let's see if it runs for this. Yep, it runs. Let's submit this and hope for the best. Okay, we are getting, oh, okay, we have to also check if if there are no values, then we will just return -1, right? Yep, I almost forgot that. Let's see now. Okay, we are getting overflows here. Let's see why. Let's make them let's see what happens now. Yep. Yep, we were accepted. Right. Now, I hope you understood the approach, right? What are we basically what are we doing? We are just iterating over the answer. We are just binary searching over the answer. Now here the answer will be a value which will be the minimum cost of any edge the graph has, and then after removing all the other edges, we will check if we have a valid path in the graph. If so, then that value will be valid. Now that value will automatically approach any of the edge values, and then that edge value will be answer. Yep. So yeah, I hope you like this approach. Also, please drop down any comments or any questions you have. I would be more than happy to discuss them with you. So yeah, thank you for watching this video, and bye. See you with the next one.